everyone, welcome to the second part of lesson 2.2. This is video 2.2.2. So now we're going to look at an example problem for the integrated rate law. So the data for the decomposition of N2O5 is given here. So here's our time in minutes, and then here's our concentration of N2O5, and here we're going to find the natural log and the inverse of the N2O5 concentrations. Remember, we don't need the chemical reaction here because the products don't matter in rates, so we only care about the reactants. Okay, the first thing we're going to need to do is fill in these boxes. So all you need to do is calculate the natural log of the concentration of N2O5. So you would just plug this in your calculator, ln 2.08. I'd like you to go ahead and do that for this whole column, and then also go ahead and plug in the inverse, so go ahead and write 1 divided by the concentration of N2O5, and then fill in this whole column, and then come back and check your work. So these are all of the numbers that I came up with when I plugged them into my calculator, so double check that you have all of your answers there. Okay, so the next step is to go ahead and use this data, or these calculated numbers, to plot 3 graphs. So we're going to plot just the pure concentration of N2O5, the natural log of N2O5, and the 1 over, so the inverse of N2O5, all versus time. So you're going to use your time versus whatever one for your graph. And this is just to see which of these graphs is going to come out with a straight line. So if you go to the very bottom of the page, there are 3 graphs for you here. I would like for you to label this one just the pure concentration of N2O5. Here's your natural logarithm of N2O5. And here's your 1 over concentration of N2O5. So go ahead and plot your data right there, and then come back and check. Okay, so after plotting data, this is what I got. I just went ahead and plotted it on a computer and printed it. You can do the same thing, or you can just plot. And we can see here that we have 2 curved lines and 1 straight line. So right off the bat, we can tell that this line right here is straight, these 2 are curved, so that means that this is going to be a first order reaction, because if you'll remember, the natural logarithm of the concentration will always yield a straight line here. And our pure concentration, if this was straight, it would have been 0th order. If this was straight, then this would have been 2nd order, but they're not. So this is our first order reaction, and that's how we can tell, just because it's a straight line. So going back up, write the rate law and the integrated rate law for this reaction. So we're just going to write here that the reaction is first order because the natural logarithm of the concentration of N2O5 is linear. So we're going to use our first order equations. So first, writing the rate law, that's the one where you have rate equals and you have a K in there. So rate law is rate equals K, always don't forget that K, times the concentration of N2O5. And since it's first order, we write a little 1 there. We're going to write the integrated rate law, which if you look at the previous lesson, you'll have a nice summary with your integrated rate law written there if you've forgotten it, or you can check the back of your periodic table. So ln, or natural logarithm of N2O5 at time t, we're replacing that generic A now with the chemical we know we have, minus natural logarithm of that same chemical, N2O5, at time 0, and that's going to be equal to negative kt. Okay, next step, what is the value of the rate constant k? So now we're going to solve for k. So here you have to know that your k is equal to your negative slope. K equals a negative slope, or negative m, as we saw before. And we're going to choose 2 points. Choose 2 points to calculate slope. It doesn't matter which 2 points you choose. I'm just going to go ahead and choose 3.07 0.732, so that's my first point. So 3.07 is that time, and 0.732. Notice that I'm using the point for the concentration under natural log. I'm not just using the concentration there because I know it's first order, so I need to use this version of our numbers here. Okay, so that's my first point, and I'm just going to pick this point also here, right in the middle. Also, I don't want to deal with a negative number. So let's see, 14.45 and 0.307. Again, you could have picked any 2 points there. All right, so doing my calculation, K is going to be equal to my negative slope. So that's going to be negative, and then y2 minus y1 over x2 minus x1. So I have my 0.307, which is that point here, minus 0.732. Over 14.45 minus 3.07. And then plugging this in, I get a negative 0.0376. And then canceling out this negative, negative, and negative, that's going to give us a positive. So 0.0376 inverse minutes. So our time was in minutes there. So we're going to have inverse minutes for our units. And if you're not sure what the units are of K, so if you go back to that summary from the previous lesson here, you'll see that this one is seconds, inverse seconds, but we're given minutes, so we're going to cancel out seconds, and we're just going to write minutes. So this is our K, and we can use this to plug in to solve for other things in that equation, like the concentration of N2O5 at t equals 0 minutes. So for here, I'm going to choose any t to plug into my calculation. So choose any time. Choose any t. I'm going to choose, so I chose t equals 31.28, right at the end of our data here. Okay, so writing my equation, ln N2O5 at time 0 equals ln N2O5 at time t plus kt. And that's just my integrated rate law that I wrote up here. All I did was copy it down. So what are we solving for here? We're solving for the concentration of N2O5 at time 0 minutes. So this really is just what we're solving for. That's it. I have everything else to plug in. So natural logarithm of N2O5 at time 0 equals the natural logarithm at time t. So ln at whatever my time t was. So I chose my time being 31.28 minutes, and I chose my natural logarithm of my concentration based on that time, so whatever matches with it. So I have negative 0.329. So I'm just going to plug in that point, negative 0.329, and that's at my time t that I chose already, plus the k. We already calculated our k up here, so our k is 0.0376 inverse minutes, and my time t, well, that's just the time. That's the other point right here. We already have that. We chose that, 31.28 minutes. And of course, these units are going to cancel out here. We end up taking the natural logarithm of both sides. So I'm going to go ahead and combine these, combine all my terms, do all my math, and take the natural log of both sides. Or sorry, not the natural log, the e of both sides. So that leaves us with the concentration of N2O5 at time 0 equals e to the 0.847. And plugging this into your calculator, use lowercase e. Don't forget not to use, that capital E on your calculator. That means something else. It's for scientific notation. So you end up getting your concentration to be equal to 2.33 molar. So that's your concentration of N2O5 at the very, very beginning at time equals 0. I would like you to use that data and the previous calculated data that we got to calculate the concentration at time equals 10 minutes, and then come back and check your work. Okay, we are going to use our same integrated rate law equation here. So the one that we wrote at the beginning, so natural logarithm of n2 05. And instead of saying at time t, we know the time, so we're just going to write at time 10 minutes here, minus natural logarithm of n2 05 at time 0 minutes equals negative kt. And that's just our integrated rate law for our first order reaction. Okay, and so then just moving on here, we're going to rewrite this part, n205 minus, and we already calculated the natural log, or we actually already calculated the concentration of n205 at time 0. That was our previous answer in our last problem. So natural logarithm of 2.33, and that's going to be equal to negative kt. And remember, we calculated k above, right up here, so there's our k. So we have negative, and our k was 0.0376 minutes, inverse minutes. And the time we're asking about here, or the time we're studying, is 10 minutes. So we're going to write our 10 minutes in there. And of course, inverse minutes and minutes will cancel out. So let's keep going. The natural log of n205 minus the ln of 2.33 is 0.847 equals, and then just carry everything else down. Gives us the natural logarithm of n205 at 10 minutes. Rearranging everything, doing all of this math and rearranging and adding to this side, just doing basic algebra here, is going to make sure that, or is going to give us 0.471. That's equivalent to this side of the equation. And then to get rid of this natural log, we take the e of both sides. So e cancels out natural log, and 205 at time 10 minutes equals e to the 0.471. And when you plug that in, the concentration of N2O5 at 10 minutes is going to be equal to 1.60 molar. And that would be your answer. And that's how you would use the integrated rate law. Okay, guys, so that is the end of lesson 2.2 and the end of video 2.2.2.